Orco. I do want to point out, because it's across all classes, make sure if I don't give you a scale, like if I just give you a blank XY thing, you put values on. You put 1, 2, 3, 4, or you can count by 2s, you can count by 4s, because scale will change. All right, on this one, I see it has to be negative x for x is less than 0. I see it has to be x plus 1 for whenever x is greater than or equal to 0. So what I'm going to do is I'm going to put a dashed line at 0. Because I know something happens on the left-hand side, because that's where my x is less than 0. And I know something happens on the right side, because all these values are where x is bigger than 0. Well, when my x values are less than 0, i.e. negative 1, negative 2, negative 3, negative 4, I'm supposed to use the graph negative x. I know what the graph of negative x looks like, but let's pretend like we don't. And we just, why are the chairs all messed up? Sorry. Anyway, if I don't know what shape this looks like, the values I'm going to pick to check it are going to be 0, because that's the line. Then I'll pick negative 1, negative 2, negative 3, negative 4 until I know what the shape of that graph looks like. So when I plug 0 into negative x, I get 0 out. I'm also going to note, because it's strictly less than, I'm going to use an open circle. Let's do this in green. So we're going to do an open circle at 0, 0. Now let's plug in negative 1. If I plug negative 1 in for negative x, it becomes a positive 1. Negative 2, take the negative of that, it becomes a positive 2. And so that graph right there is my f of x equals negative x right here. And it's on the left-hand side. On the right-hand side, I need to plot x plus 1. Once again, I'm going to start at where the dashed line is, so that's 0. I'll plug 0 into x plus 1, that's 0 plus 1. Since it's on the dashed line, I just have to ask myself, is it closed or open? And it's going to be closed because it is greater than or equal to, so I'm going to close at 0, 1. Then I'll plug a 1 in, because 1 is definitely bigger than 0. That's going to be 2. 1's going to go to 2. If I plug a 2 in, it's going to go to 3, so on and so forth. And I'll just have this straight line right there. That is my piecewise function. Questions on this? Cool. Questions on the homework? There should be, because several of you have pointed out stuff that was wrong, but you don't have questions.
All of them?
Can you just go through the first one to the last one? Very, very slowly, because I might not have much of it done. Come on, questions. Someone's got to have questions. Yeah, Fatima. 71. Thank you. I think I had 71 up there. So 71. So our big thing when I'm going backwards, what I want to look at is where's the changeover. All right, where do I switch functions at? Let me try it in purple, see if that shows up. So I'm going to draw a dashed line just like I would if I was actually drawing. I'm going to draw a dashed line at x equals 0. So something happens to the left of x equals 0, and something happens to the right of x equals 0. So let me just label this. So this side would be x is less than 0. This side would be x is greater than 0. Well, we have two different functions happening here. I have the function that will give me this line, and I have the function that will give me that line. So let's find the functions first. So since I'm dealing with two functions, that means it's a piecewise. And I'm going to say f of x equals, and I'm going to put my first function here and my second function there. Well, these are just lines. So to come up with the equation for a line, I can either use the point slope form, which is y equals mx plus b. I'm sorry. Point slope form would be y minus y1 equals our slope m times x minus x1. What would be easier, and in my head I was thinking this, I'm going to use slope-intercept form. Slope-intercept form is y equals mx plus b, where m is my slope, b is my y-intercept. So all I need to do is find my slope of my line and my y-intercept. So if I look at this first line, Our slope is always rise over run, so this goes down 1 over 1. So the slope is -1. And my y-intercept is going to equal a -2. So the equation for this line is y equals a -1x or negative x minus 2. Probably not the best place to put it. It gets a little jumbled. But do you see where I came up with that y equals -x minus 2? So I'm just going to write that here. I'm just going to write that -x minus 2 because the y is taken care of from that fx. Now I just have to say where it occurs. And I'm going to say where x is less than 0. Here's the thing. I can actually use less than, or I can use less than or greater than, because there is a closed dot here. So if I said x is less than or greater than 0 here, my next one would be where x is greater than 0. Or I could flip the equal signs. That's what you're about to ask, right? Yep. Because no one knows. You're the one coming up with it. One of these has to be closed here. Yep. So I could have flipped it.
Could you make them both closed?
I could technically. Yep. In this case, it would. I would choose not to, just because 90% of the time,
It's not.
because if they're not overlapping, they can't both be closed.
Yeah.
So I just, in my head, always think one's closed, one's open. But yes, it would work if they're both closed because it would stay a function because they both were closed at the same point.
So would we lose points on the test if we made them both closed? Or okay.
Nope. It's just nice to get in your head a nice little pattern that one's open, one's closed. One's open, one's closed. So on this one, although they could both be closed, it's nice to go, okay, one's open, one's closed.
It's so weird that like if it includes it, then it's closed because you'd think that it's like it can't do that.
Like you can't.
If it's open, nope, you can't have.
No,
it.
you
It's
can't
like-
go in the open place.
Yeah.
You can go in the closed place.
Exactly. It's like no.
Maybe I should come up with a new name for it.
Well, this person clearly made it on April Fool's Day, so it's like.
All right, other questions on either this? I didn't quite finish it. I'll let you finish that other one. But were there other questions from the homework?
Is tonight's homework difficult?
No. All right, if there's no questions for me, I do want to go over one because several of you had it wrong and no one decided to ask on it. First of all, this one is a semicircle. It is a semicircle, and I know it's a semicircle because I could have just plotted points, or I could have noticed that if I'd square both sides, I'd end up with y squared equals 9 minus x squared. Anytime you have an x squared and a y squared, it's a circle. But it's only half the circle because I don't have the positive or negative. If I had positive and negative, it'd be a full circle, but this is just the positive portion of it. The other way, let's say I didn't even realize it was a circle. Like my brain's just like, I'm on a test. I just want to plot points. There's only so many points I can plot here because it can't be negative. Anything under square root cannot be negative. And because of that, 9 minus x squared must be bigger than or equal to 0. There's two values that make this equal to 0, and that is a positive 3 and a negative 3. Anything bigger or smaller will not work because 4 squared is 16. 9 minus 16 is a negative number. So 3 and negative 3 are the biggest numbers that we could plug into this. So we could either use a negative 3 or a positive 3. And I'm just going to check right smack dab in the middle at 0 to see what just plugging points in does. When I plug negative 3 in, it gives me out 0. When I plug 0 in, I get... maybe I'll actually put this in here. 9 minus 0 squared, which is just going to be 3. This one will get me 0. So I'm going to make my mark negative 3, 3, positive 3. I'd have a point here, point here, point here. Either it does this, which doesn't make any sense because we don't really have any functions that do that except for absolute value. So more likely it'd be a nice, that was not nice, was it? There we go, semicircle. The other one I really quickly want to go over is the one right before it. This one creates kind of havoc because x cannot be 0. So at 0, nothing can exist. So the only thing that can be there is an open circle. The only thing that can be there is an open circle. So let's see what happens on the left-hand side of it and the right-hand side of it. Let's try values. So we're going to make our little t-chart. If I plug in, say, a -2. If I plug in a -2, I would have the absolute value of -2 over a -2. Absolute value of -2 is a +2. 2 divided by a -2 is a -1. If I plug a -1 in, it's a similar situation. I have -1 over -1. That's going to turn into a -1. In fact, if I throw in a -0.001, I'm going to once again have absolute value of -0.001 over -0.001, which is going to be -1 again. Any negative value I plug in, I'm going to get a -1 out. How that's going to look on the graph?
And any positive thing you plug in will be a positive one.
Nailed it. So part of my graph is going to look like this with an open dot at 0. And if I put a positive in, so say I put in 1 or 2, I would get a +1 and a +1 out. So that would look something like that with an open dot here. That changes your domain a bit. Your domain is no longer -infinity to infinity because you need to stop at 0, not include 0, and then continue to infinity. Range would just be 1 and -1.
Is 0 over 0, 0, or 1, or undefined?
0 over 0?
Yeah.
It's divided by 0.
Here's the way I look at it. If you're a guy at the beach, right?
Yes.
You can have no shirt with shorts on. So that's a 0 over any number. You can't flip that. You can't have 0 on the bottom.
Unless you go to southern Italy.
If you go to a normal beach, you can't have 0 on the bottom. 0 is always undefined. All right. Yes?
Never heard that one before.
I was gonna put 1 for 0, and then I was thinking about 0 divided by 0, and I remembered if you ask Siri what 0 divided by 0 is, she gives you a really sarcastic and mean answer.
Oh, does she really?
Yeah, and then I'm like, oh right, you can't do that.
Okay, besides what Siri says, let's go into today's lesson. Today's lesson is not earth-shattering, crazy new. We, in fact, already did it this year. It is transformations. And it is easier transformations than what we did, because we did transformation with sine, cosine, tangent. If you remember our transformation with those, we always had to find the period. We had to mark down the period, kind of do that half multiplied by 3 to get all that stuff straight. We don't have to worry about that. All we have to worry about is going up, down, left, right, flip, stretch. Those are the only things we're going to be doing today. So it is yoga. It's math yoga. All right. So the first thing we're going to talk about is vertical. A vertical translation, that is just going up or down. The two ways, not the two ways, the two different directions we can go is up and down. To go up, we're going to take our parent function and add a number to it. What I mean by taking a parent function is like square root of x squared, absolute value of x, and then you just tack a number on outside of it. So anything that's happening outside the parentheses. If you remember, like when we had sine of x, if you would add 2 to it afterwards, it would go up 2. Once again, if I add a number just outside of the parentheses or outside of the parent function, that is going to go up. If we have f of x minus k, that is going to go down. So my examples are down below. I have x squared plus 2. I also have x squared minus 3. If I have x squared plus 2, that plus 2 is outside of that x squared, so that's going to tell you to go up 2. And it's not exactly rocket surgery. We just have to move every point up 2. So if I have the point 0, 0, I add 2 to my y value to give me 0, 2. I literally just go up 2. Let's go to the next one. We could move this up 2. I guess we'd move this one up 2, which is a little off our graph, but we could see it. And we do the same thing to the other side. So it looks something like that. So that graph right there is that x squared plus 2. All right, the next one is x squared minus 3. That means I just got to move everything down 3. So I take my parent function, which is x squared, which is that black line, move every point down 3. So I count 1, 2, 3, boom. 1, 2, 3, boom. 1, 2, 3, kazam. That one goes kazam. I don't know why, it just does.
No. Now I know why we'll hear a bunch of kazams during the test.
Kazam.
That one on the end just makes a noise.
And that is my x squared minus 3. And maybe I'll put a little arrow saying it went down because it's the negative 3. All right, next one is horizontal. It shifts the graph up or down. That doesn't make any sense. It shifts it left or right. That is a copy and paste error if I've ever seen one. So we need to go left or right. Kind of like when you like the format of something, you copy it and you paste it somewhere else and you forget to change all the words.
I've done that in emails. It's so awkward.
Emails are the worst because once it's sent, it's sent. It's like, I want it back. Can't tell me you never wanted it back. All right, to go left. All right, let me put down the two possibilities first. We can grab f of x plus h, so the h is now inside the parenthesis. Or we have f of x minus h. If you remember from sine and cosine, yeah.
Plus moves left and minus moves right.
Yep. If it's inside the parentheses, it goes the opposite direction. You think it does. Plus is going to actually go left. Minus is actually going to go right. So that means that x plus 2 that's in that parentheses is actually going to make it go left. And that one that's negative 3 inside is going to make it go right. And it's going to blow your mind to hear that we just need to move the points left for the first one and right for the next one. So our x plus 2 squared, we just shift all of the points 2 places to the left. We just shift everything over. It looks something like this. Bless you.
Thank you.
So this graph here is that x plus 2 squared. To move it to the right, we just shift all the points to the right 3. So 1, 2, 3, that would be my first point. 1, 2, 3, boom, boom. I guess 1, 2, 3, kablamo. I don't make the sound effects up. I just know them from a mathematical standpoint. That if that point were to make a sound, it would have to make that sound based on math and physics. Oh, you don't want to know. All right, that's just left, right, up, down. Did I blow anyone's minds? Is this too complicated? Should we just stay here and just... I'm sure you're all like, yeah, let's just take a test on this.
Put them in the wrong places.
I want to put a...
Doesn't x minus 3 go to the left?
Oh,
Am I wrong?
you are wrong.
I thought he was right for a second. But
No.
you looked for a second like.
I thought plus...
They go opposite directions.
Oh, my right.
Yes, you just put them in the wrong spot. Plus tells me left. Minus tells me right. Cool. So negative 3 should go right. 3. All right, the next one is reflections. Reflections across the x-axis, reflections across the y-axis. To reflect across the x-axis, all you're going to do is throw a negative sign in front of your parent function, as exemplified by that negative absolute value of x. Absolute value is my parent function. negative I threw outside of it. So down below is the parent function absolute value x. Since the negative sign is out front, what I want to do is I want to reflect all of those points across the x-axis. Well, 0, you can't reflect it. It's already on the x-axis. I'm going to, instead of negative 1, 1, I'm going to have negative 1, negative 1. And then I'll flip the next points down here. And the next points. I really don't need to do all of them. But it's going to be a reflection across the x-axis. This is my negative absolute value of x. So if I tack a negative sign to the outside of the parent function, it flips it one way. If I tack it on inside of the parent function, it does something slightly different. So that's going to go across the y-axis. So that's going to be f of negative x, which is shown there. Well, that means, since I have the negative sign in here, and this is my parent function square root of x, instead of reflecting it like this, because it's inside, I'm going to reflect it around something like this. Let's color it blue. So I'd have a point there. I'd have a point there. And I'd have a graph that looks like that. Yeah?
Can you flip it both? Like
Sure.
That line, can you do like that?
What if I did h of x equals a negative square root of negative x? I would do both. It would actually go whoop, whoop, maybe down here. Yes?
I have a question about the horizontal one again.
Uh-oh. Are we going left, right, or up or down?
Both.
Okay.
Or no, sorry, the left, right one. I was
Okay.
sorry, okay. Wait, why would subtraction go to the right?
Let's put in a value. So x squared, 0 equals 0, right?
Yeah.
All right. Well, if I plug a 0 in for this one, I'd have 0 plus 2, which would go all the way up to 4. I actually have to shift over to make this into 0. I need to plug a negative 2 in here to get back to 0 squared. Do you get what I'm saying?
I think so.
So normally if I plug in, let me pull out a... So if I have x squared, right?
Yeah.
And I'm plugging in numbers and I have x. If I plug 0 in, I will get 0 out. Well, the only way to get 0 out if I have x plus 2 squared is to actually plug a negative 2 in, then I get that 0 out. So that shifts everything over 2 to get the same values out.
Okay.
Just remember, if it's inside the parentheses, it goes the opposite direction. If I'm adding, it goes left. If I'm subtracting, it goes right. And you can always plug in points. If you're not sure on the test, just plug in a point and see if it works. All right? All right, then we did flipping. Now we're going to do vertical stretch, vertical shrink. Vertical stretch and vertical shrink both happen outside. They are being multiplied instead of adding. So a vertical stretch is going to have some number a times my parent function, but so will a vertical shrink. However, our a values are going to be different, and it'll tell me whether it's a stretch or a shrink. To be a stretch, it is going to be where absolute value of a is bigger than 1. For it to be a shrink, we need our absolute value of a to be less than 1. So basically anything between 0 and 1. So if you look down there, it's 1/2. That's a shrink. 2 is going to be a stretch. Now, vertical stretch and shrink, people tend to mess these up a bit. And I'll tell you how they mess it up. So,
I could probably figure it out.
yeah, we'll look at Nick's test and we'll see how it. No.
Pretty much.
No, if you just pay attention now, you'll get it and you'll be fine. With vertical shifts, they go up and down. You add, so if we look at this one, I added 2, which meant I boosted every point up 2. That is adding 2. I add 2 to the height. With vertical stretch, I am going to multiply to get my height.
So it's the width.
I'm going to multiply. No, it's still height. It's still going to affect our height a little bit. You'll see. You'll see. And so we just look at the points that we have. So I'm looking down here. All right, that is the point 0, 0. If I was adding to it, I would just add 2 to it, but we aren't. We're multiplying. What's 0 times 2? 0. This point will not move. The points along the 0 do not move. And I kind of think about, like, if I'm stretching something, I hold one hand steady and I stretch out. So I'm grabbing the top and stretching it out. It has to stay down here at our zeros. All right, the next point I want to look at. The next point I want to look at is this point 1, 1. And I'm just looking at the y value because I'm stretching it up. All right, so we're just looking at the y value. What we're going to do is we're going to multiply the y value by 2. We multiply it by 2 because we have a 2 times. So we're going to multiply it by 2 to give me the point 1, 2. I'm going to skip a point because there's not a lot of room here. And I'm going to go right here. That is the point 3, 3. Once again, I multiply the y value by 3 to give me the point 3, 6. And I could do the same thing in this next point is 4. The y value is 4. 2 times 4 would give me, oh, I pointed too high, 8. My next point would be the point here, which would be 4, 8. So I'm just multiplying the y values, and that's going to create a line that looks like that. I guess I should put an arrow on it. And we're going to do the same thing for the other side. Multiply everything by 2. And we're going to end up with a line that looks like that. And that is now my 2 times absolute value of x. So it pretty much tells you what to do. Multiply by 2. With vertical shifts up and down, you just add the number to your y value. These you just multiply by the value. So in fact, bless you, you don't even need to remember if it's a vertical stretch or a shrink because the multiplying does it for you. You don't have to think about it. And the next one I'm multiplying by 1/2. So if I look at, do I stretch 0? Is that going to move? No, because I'm multiplying by 0, so that's going to remain. However, my next point is the point 1, 1. I'm going to multiply the y value by 1/2, which will give me the point 1, 1/2. I guess the next value I'd look at is maybe this 4 up here, which would be the point 2, 4. I multiply that 4 by 1/2, and I am going to get out 1, 2. We have something that looks like that. Let's do it over here. Something that looks like that, and this is the graph of 1/2 x squared. Those are probably some of the most missed because people end up moving that 0, 0. They'll like move it up 1/2 or something, and they'll think they need to add 1/2 to everything. It is multiplying your y value by your stretch factor. Questions on either one of those two, now's the time to ask, not during the test where you're like, I don't know how to stretch it. We okay? We doing okay? That's it. That's all we're doing today. Well, I'm going to show one more example, but that's all we are going to worry about today. We're going to worry about up, down, left, right, reflections, and then is it getting stretched or shrinking. All right. when I put a multitude of them together, we have orders that we're supposed to adhere to. First thing we're supposed to do is we're supposed to do our horizontal. Then we're supposed to do our stretching, then reflection, and then our vertical translation. I really don't care which one of those first three you do first. Those first three you can pretty much do in any order and you're going to be okay. The big one is this has to happen last. There's gray area here. You can do reflection first. You can do your stretch and all that kind of stuff. If you do this one out of order, you're going to get the wrong graph. This has to be done last. Has to be done last. So I don't care if you don't memorize this stuff. Know this has to be last. So when you're looking at this, graphing more than one thing, just know your vertical goes last. Vertical goes last. All right, let's apply everything we know to this. Well, we have a parent function of square root of x. The first thing I'm looking at is I'm adding 1 inside the square root. And as Luke knows, adding 1 inside is going to actually make it go left 1. So that's going to make it go left. This 2 out front is going to be a stretch, because I'm going to multiply those values by 2, which is going to stretch it. This negative down here is going to be a reflection. And it's actually being a reflection across the x-axis. And this 4 is going to make it go up, because I'm tacking on a positive 4. Remember, the last thing you care about, the last thing you can do is up, down. So really the only thing I care about is do this last. I'm going to do it in the proper order because that's what I showed before, and it's class, it's your notes. But just know that this has to happen last. That's the only one that's really important. All right, the first thing I'm going to do is I'm going to draw the parent function. The parent function is square root of x. Square root of x has the point 0, 0, 1, 1, and 4, 2. This is my parent function. I should probably note that this is square root of x. Per the notes, we're supposed to do horizontal next. So we'll do our horizontal shift next. I said we're going left 2, or 1, sorry. We're going left 1. So let's go ahead, and I'll just do this in red. I'm going to move all the points to the left 1. Boom, 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 boom. Chicka, chick, 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 chick. We now have the graph of square root of x plus 1. I'm going to move to the next graph. The next thing we're supposed to do is our stretch. So we're going to multiply all those y values by 2. The only one that's going to stay put is that guy right there, because it's our 0. I'm multiplying 0 by 2. So let me go ahead and do this in green on the next graph. I don't care what I just gave you 3 graphs. You can put them all on one graph if you want to. I'm just going to put it over here, and I can't change that side because that's one holding place. The next thing I'm going to look at is this y value of 1. Multiply it by 2. It's going to go up to 2 now. The only other point I have is at this 3, 2. Multiply that 2 by 2, and that's going to go up to 4. So this graph right now is a square root function where it got shifted over 1 and stretched 2. Now we're going to handle that negative sign. The negative sign just reflects it across the x-axis. So these points are all going to get flipped down there. All right, so we're just going to flip it down there to take care of that negative sign. What color haven't I used? Ooh, a really ugly brown. I like it. Maroon? What color is that?
Not ugly.
Not as pretty as green. All right. Ooh, ooh, ooh.
It looks good with the green.
Oh. I missed my mark on that one. That one should be at -2 because all I'm doing is I'm flipping down. It's going to look like that. And this is a square root of x function where I went over 1, stretched 2, and I flip with that negative sign. The last thing I have to do is at 4, which is just moving everything up 4 points. So I'm just going to shift everything up 4. So my first, what color should I pick? All the colors, just rainbow. Oh, I wish I had rainbow selection. I don't think I use this one much, but we are going up 4 on all of them. So that one's going to be up there. Our other one shifting up 4 is going to be at this 2. And the other one was at -4, 3, -4. So instead we're going to have 3, 0. This feels like a very Eastery color. Is that just me?
Yeah, no, I feel you.
This is my 4 minus 2 square root of x plus 1. All right, the homework isn't hard, or shouldn't be. It's not made to be. I'm not saying that you might not struggle on it, and you can ask questions, obviously. But I want to point something out to you. All of them have just a blank grid on them, and it has a good reason for it. I'm going to give you an example that isn't on here. Let's say this one was negative, 12. I'm going to think in my head, hey, I need to move over 12 units, and I'd be going down 12 units. Well, 12 units might be hard to count out, but what you can do, knowing that it has to go down 12 units, is to make your XY plane a little higher. Like put there and there. Now I can count by 1, 2, 3, 4. If I count by 2s, I would start down here. All right? I want all of your graphs to be on here. I don't want to see this. I don't want to see this where you're like, okay, it's shifting down 12. I don't care. I'm going to put this right smack dab in the middle. And I'm going to count everything as 1, so I'll do -1, -2, and then all of a sudden you try to drop it below the graph. All right, like way below the graph. I don't want you extending stuff. You need to pick a proper scale and a proper place to put your XY so that your graph can fit on there. All right?
So then should we do like each step in a different color?
You can't. All of them are just 2 steps. They're the parent function and the shifted ones. You don't even have to use different colors.
Oh, so it's not going to be like a 3 shifts.
That's nice.
I forget which one. There is some that have it, but for majority of them, they're just shifting
Alright.
1.
Like 15.
Yeah.